My name is Mark Benevides. I work for Siemens Building Technologies. I've been with them for going on 35 years, which means I started when I was 5 years old. We're going to be talking today about chilled water system optimization. This is a solution that we have, that Siemens has, that's essentially was rolled out in 2004, which was the very first facility that we implemented this on. And then we've taken this internationally about 4 years ago, and now we are doing projects all over the world through our Siemens offices, anywhere from Dubai to Hong Kong, Australia, pretty much all over the world now. So we're going to talk about chilled water plant optimization. Generally speaking, chilled water systems are one of the most energy intensive components of any facility. We talk about optimization in terms of a holistic approach to the chilled water plant. So we don't just focus on the towers, we're not just talking about the chillers. There's a lot of products in the marketplace, a lot of companies that do an excellent job at individual components. What we try to address when we do a project is we address the entire system. So what do we know about chilled water plants? We know that most chilled water plants that we face in the marketplace today have some form of constant flow pumping. Most plants have a bypass on the chilled water flow, which is indicative of excessive pumping energy. If there's water going through that bypass, you're pumping too much water, essentially. We know that plants operate best with wide temperature splits across the chiller, certainly at or near the design intent, what we call the delta T. We also understand that plants work at those design intents typically only about 5% of the time, right? As an engineer designs a system, he's designing it for that hottest day of the year, that design day. That plant has to be able to deliver that chilled water for that day. The last thing you want is a building that can't deliver the cold that you need on those design days. But that only represents about 5% of the time. So what happens the remaining 95% of the time? And essentially that's where we take advantage of that 95% of the time and find ways to optimize the plant. Most buildings we walk into today, I can say this, I actually visited a site here in Orlando yesterday, walked in a plant that had a 12-degree design delta T. It was operating at 3.5, right? That's not uncommon at all. Most of the facilities that we see are suffering from what we call the low delta T syndrome. They're inefficiently operating then 95% of the time due to design. And I want to qualify that. That does not mean that the design was poor, but the design intent always has to meet that design day. And since that represents only 5% of the year, 95% of the year, those plants typically are not operating efficiently. The industry has tried to resolve these problems with limited success over the years. We tend to focus on one part of a plant without understanding that when we do that, it has an impact at other parts of the plant. So often, one of the other things that goes on is that we will provide some energy efficiency, but we sacrifice comfort. And that's not the case with what we're talking about today. Our first and foremost priority is always occupant comfort. We will never sacrifice efficiency for comfort, or if it's a manufacturing plant, for whatever conditions they need for their production. We also realize that nominal plant capacity is usually never realized, causing perceived need for additional chillers. About a year and a half ago, I was at the Dubai International Airport. They have 4 large chiller plants on that airport property. The largest has 36 2,000-ton machines, 72,000 tons of refrigeration. They have a large primary, secondary, tertiary system there. I can walk through the condenser water piping standing straight up. I mean, this was a big site. They were having problems, though, delivering chilled water to their air handling units in the terminals. And so their solution, if you can't get the water to the air handling units, what do? You turn on another pump. That's what the thinking was. When we analyzed that plant, we realized that they were pumping over 7 billion gallons of water more a year than was necessary. That water was essentially just circulating within the primary loop, constantly coming back, not doing any work out in the field. So they were running chillers, more chillers than they needed, more pumps than they needed, hugely inefficient. And this is something that we see quite frequently, because in most cases people feel, hey, if I can't get that chilled water to the coils, it must be I don't have enough pressure, I don't have enough flow, let's turn on some more pumps. And what we're going to talk about resolves those problems. We deliver only the amount of water that we need to meet the load at any given time. That's what demand flow does. Demand flow essentially is a variable pumping system, variable flow pumping system that balances the flows between primary, secondary, tertiary. If you have a variable primary system, we can work with that as well, and we can optimize the flow to meet the load as opposed to an arbitrary pressure set point. So we understand there's 5 subsystems of a chilled water plant that consume energy and influence capacity, right? The chilled water pumps, condenser water pumps, the chillers themselves, the cooling tower fans, and if we're talking a VAV system on the air side, then that also counts as a subsystem. We recognize that these 5 subsystems are interdependent. If I change one, it's going to have an impact on the other, which is why when we talk about energy optimization, we talk holistically, because it's very difficult, quite frankly, to just focus on one of these subsystems without understanding what's happening to the others. Often conservation methods reduce deliverable system capacity. I've been in this business for 34 years, 35 years, and I still see specifications that come across the desks of some of our engineers in which say, on cooler days, raise the chiller set point temperature, right? Because I don't need that cold of water. And in some cases, that makes a lot of sense because you will save energy at the compressor on the chiller. However, in a large VAV system, what we have found is that those VAVs now have to operate a little harder because they have to push a little bit more air because the water going through the coil is warmer. When we do that net-net comparison of KW, in many cases we find that that strategy is actually counterproductive. We find that we're actually using more KW when we raise that set point than we would have if we had just left it alone. Now that's not saying every project is like that, but I would say about 70–75% of the projects that we've run into, that is the case. So there's a lot of things that happen in ways we've approached plant optimization in the past. And demand flow, our solution of variable flow pumping is quite unique. It is patented. There's a number of patents that we have, that are involved in what we do. And right now we have about 400 projects around the world, the vast majority of them here in North America, in the United States, and in Canada. So often what is done in the name of energy conservation results in a transfer of energy. That's basically what we were talking about, right? It's very important to understand what energy is used by each of these subsystems, how that energy is used, and how do we write then our control sequence to optimize that at any given load. And when you consider that load is constantly changing in a facility, this is something that has to be done in real time, that calculation. So what is different? What do we do differently? Effectively, we establish only one chilled water loop, virtually no bypass. Water flows through the chiller, varies through the chiller and the condenser barrels on the machines. So we vary the flow through both the evaporator and the condenser. We put VFDs on all the chilled water pumps and condenser water pumps and on all the cooling tower fans. VFDs are not required on the chillers. However, if you have VFDs, we can take advantage of that and generally get anywhere between about 6 to 9%, 6 to 10% additional savings, depending on where that chiller runs once it's loaded. We optimize the pressure and temperature set points on the chilled water and condenser water based on current system dynamics. So essentially, we are constantly looking at the load in the facility and based on that, determining what our flow set points should be and deliver that amount of water. We're looking at the water that's going through our bypass, and essentially, we want to eliminate that. When we have one of these systems balanced, effectively, you're talking about a few percent of the overall water going through that bypass. In many projects, we have a automatic valve on the bypass line, and we'll just close that bypass line completely and only open it when we are concerned about minimum flows back to the chiller. That's quite frankly the easiest thing to do, and it's very effective. So we can increase the system deliverable tonnage. How do we do that? I mean, it's pretty simple. By varying the flow of water through that evaporator coil, as we slow that down, the heat transfer as it's going through that evaporator improves. So the useful refrigeration effect of that machine increases. It's not uncommon that we can increase that refrigeration effect by about 10 to 20% in that range, depending on how slow we can slow down the flow based on the load at any given time. That surprises a lot of people. The very first project we did was at a casino hotel resort, the Beau Rivage in Biloxi, Mississippi, back in 2004. And the customer was not interested necessarily in energy savings. He was having a problem with load in his building, and essentially had shut off all the back office support areas from air conditioning because he needed to make sure that the air handling units serving the casino and the hotels had as much chilled water as they could get. And he came to us and he said, hey, we had a long control relationship with the customer, and he said, is there anything we can do? And we said, well, we've got this solution. It's new. We've tested it, but we haven't really tried it in a real live building. And we said, hey, we'd like to give it a try. He said, fantastic, let's do it, essentially. You got to realize that this building is right on the beach in Biloxi. Literally, there's no space to put another chiller in this plant, and that's what he was looking at. Additional chillers, additional pumps, piping, everything that goes along with it. He literally is on the beach. So in 2004, we implemented the project. He went from running 5 machines during the summer months at full bore to try to maintain the load to operating 4 machines after that project was done. The first year they saved around $300,000, which to him was just an added benefit. He wasn't even all that concerned about it. The interesting thing from this is not long after we implemented the project, the utility company called the chief engineer and said, hey, we've noticed quite a drop in your consumption. What are you guys doing? And he said, well, the only thing we've done is implemented some optimization on our chilled water plant. They said, well, we don't believe that that could be it. We want to come out, we're going to change the meter. He said, okay. They came out and they changed the meter, and it wasn't the meter. The customer liked it so much, it's fair to say that after 2006, when Katrina came in, it essentially flooded that entire plant, tore it apart. MGM, who was the owner of the hotels, made a commitment to the employees of the hotel that they would rebuild that plant, that facility, within a year. The second time around, it was installed with demand flow from day one. So, what do we normally see on the demand flow project? We're definitely going to see chilled water pumping energy is reduced, and depending on size of the plant, ton hours, those types of things, that can be significant. The condenser water pumping energy is typically reduced, but not always, and we'll talk about that a little bit later. Certainly the efficiency of the chiller, the kW per ton, will be reduced. We talked about airside savings are possible. I mentioned that Dubai Airport project with 72,000 tons of refrigeration in one plant. We estimated the savings of the first year of that project to be about $7 million. It was phenomenal, savings, but incredibly inefficient system, the way that they were operating it. The way it was designed was great. We estimated and tried to convince the customer that the air side opportunity was every bit as big as the water side. They had 320 some odd air handling units in the 2 terminals that this plant, and every single one of them was static, just a fixed static pressure air handling unit. So huge opportunities on the air side as well. So we will look at that also when we start talking about optimization of the plant, because obviously how you use your chilled water goes a long way to how optimized you can make that plant. Let's go move on. One of the questions that generally comes up is, what about warranties on the equipment? I tell you, about 4 years ago when we introduced this up overseas, internationally, I was responsible for that. Every country we went to, and it didn't matter what the manufacturer was, Trane, Carrier, York, Century, Mitsubishi, all said the same thing. You cannot vary the flow of water through our chillers. It will ruin the machines, it will void the warranty. You pull out their own engineering manual and it shows you what the min and the max flows are for every one of those machines. And you say, explain this to me. Well, they can't. We went through that in 2008 and 2009 when we introduced this in the US as well. But soon it was pretty much widely accepted that, yes, you can do this. It's interesting, I have a guy on my team who worked for 25 years with Trane. Great company, great equipment. But he was told there's no way you can reduce the condenser water flow through a chiller. It will damage the machine. He was also told that you could never go below 68 degrees condenser water on a chiller. As he tells it, he said, I used to have that tattooed on my arm, right? Well, both of those things are myths. You can definitely go below 68, and you can definitely vary the flow of condenser water through a machine. So the key is to understand where the min and the max levels for flow are on both the condenser and the evaporator, and making sure that you always stay within that range. If you do that, You never have to worry about overpressurization or underpressurization on the machines or any type of temperature problems with the machines themselves. Because chillers basically are pretty stupid machines, right? They know two things, temperatures and pressures. You stay within those range temperatures and pressures, those machines will work all day long. It's ironic because many times when we go out and we see plants that are operating poorly, it's because we are pumping too much water, for instance, through the condenser on colder days. And those machines are right on the level of surging. In fact, a lot of times they do. And this is one of the things that demand flow can fix. As we optimize, we not only are saving energy, but we are making sure that the conditions that those machines operate in are ideal as they possibly can be. We did a project in Robina Hospital. It's on the Gold Coast in Australia. If you've ever been to Australia, if you ever have a chance, I suggest this area. It's beautiful. We were there in their winter time, so it would have been June, July time frame. Every day prior to our arrival for the previous like 3 or 4 weeks, they were surging their machines on low load conditions. They basically had three 1,000-ton York machines, and these machines were operating at very low loads. Only one machine was on. It was operating at around 200 tons. And with the condenser water flow and the temperature that they had at that time, the machine would surge, the machine would go offline. They had to have that machine online because they had an MRI facility in the hospital that required the chilled water. But essentially, on colder days outside, that was really the only load in the facility. When we left that project after we implemented demand flow, we eliminated the surge problems. We were able to get down to about 150 tons of refrigeration on a 1,000-ton machine without shutting it down and without surging the machine. It's pretty special when you see and you hear that machine going, screaming, and then you reduce that flow of that machine down to what it needs to be, and it essentially becomes quiet. We did a project at Nashville Airport, and prior to this project being done, they were using cooling towers at the airport. They had a quarry, though, on the airport property that year-round delivers about 50 to 53 degree pond water. And it's quite a big pond, and it's spring-fed, so it's a constant supply of water. And the project was to install the piping, a loop, so 4 miles worth of piping, to take advantage of the colder condenser water. Prior to that implementation, you walk into that chiller plant with those chillers on and you couldn't hear yourself think. Loud, very, very loud. You bring in that 53-degree water right into those chillers and they just quieted right down. The efficiency of those machines went from of the plant went from just slightly over 1.2 kW per ton. We're operating that plant right now on a year-round basis anywhere between 0.35 to 0.40 kW per ton. So that 4-mile piping project, which was by far the largest cost in our implementation, they estimate that that will pay itself back in under 3 years. And that included having to go underneath the runway, which required special FAA permission and special techniques apparently on how to bury pipe and compact the soil and everything. So it was quite a project. So typically what we see on our projects, anywhere between 20 and 50% plant energy savings. Honestly, if you're talking 50%, then you've got a lot wrong with your plant, but it's not unheard of. We have seen it. Anywhere between 1 to 4 year simple paybacks is the results, often an internal rate of return of greater than 25%. We typically do all of the turnkey installation and commissioning. Many times customers say, hey, well, let us put the sensors in or let us do this, and we'll work with them. But honestly, more often than not, we're ready to go, and they're saying, oh, yeah, we didn't get around to that yet, you know, and it just becomes kind of problematic. So we ask, or we strongly suggest, they allow us to just do all the work. So we will, part of the process is we will do a baseline. So we will calculate what the energy costs are for that plant to operate. To do that, we need anywhere between 6 and 8 weeks of trend data that we collect from the plant. And that's hourly data for 6 to 8 weeks. From that, we develop the model that will determine exactly what their consumption would be. And we sit down with the customer, we review the model, we get the green light, that becomes our baseline. Then we implement the project, and then it's constant measurement and verification in real time and in every 15-minute increments. So at the end of each month, we can give them exactly what the savings were, both in in tons of refrigeration and kWh. So they understand exactly what the savings are. If you have an unusually hot month or that, we can normalize for weather, do all those types of things. But essentially, that's how the process goes. We utilize a product we call Navigator, but there's a number of systems out on the market today but Navigator is what we use to collect that data, to trend that data, and to store it. And it also then generates the reports for us automatically. Essentially what we are doing, though, prior to our latest revision of our modeling software, we would ask for 365 days worth of data. All we needed was one piece of data each day, one time, a chiller log or whatever, and we would develop these curves. We can now do that using bin calculations with, like I said, about 6 to 8 weeks. So that's been a tremendous advantage to us now as we go out into the market and we're looking for opportunities. Because within between 6 and 8 weeks typically in North America, we can tell you exactly what you're going to save, and we are confident enough to guarantee that. We essentially are able to create what we call the variable pressure logic curve. Essentially what we're doing is looking at the facility load and understanding and calculating what the set point should be for that speed drive, for the VFD. We then are able to modulate that set point based on load, and essentially what it does is it follows that dynamic variable system pressure curve. That's what we call it. Engineers would call it the building curve, right? So if you take an engineer's design, they understand exactly what happens as the load reduces in their facility, right? That curve is developed. All we're doing is saying, hey, we can deliver the cooling, the chilled water, to follow that curve under any load condition. So there is no bypass, right? So we take advantage not only of the fact that we can reduce the flow of water, but also the pressure of the water. One of the biggest challenges we face as we go out and we install these projects is that operators are used to seeing certain pressures in their building, right? And it's not uncommon that our pressures that we're going to deliver once you implement, especially on a cooler day, low load, will be dramatically different. We did a project at Florida Gulf College outside of Pensacola, or Panama City, I think, yeah. And the operator was used to seeing about 35 pounds of pressure in his secondary loop. On the day that we implemented, that went down to about 2.5 pounds of pressure. So the concern was naturally, do we have enough pressure to deliver that chilled water to that last building in the loop and to the highest point in that building? Now our BMS system was saying, yes, not a problem. We're maintaining air handling discharge temperature fine. Our valve was about 50, 60% open. But customer wanted to walk to that building and verify, which is not a bad thing to do. But we did, and everything was fine. And this is kind of what we face a lot of times. We will implement these projects. Customers don't understand what's happening from a pressure standpoint in their system, and they start panicking, and they start turning on pumps, and they start turning on additional, equipment. So part of every project we do is you have to educate the customer. What is going on? Why is it doing what it's doing? Okay, if you have any questions, how do we go through that? To that end, we have a fairly robust analytic engine that we include with our projects that looks at the conditions throughout the plant. And if it starts to see any type of red line conditions or problems within the plant, it notifies the local user, alarms if need be, and also if the customer allows us to connect this to the internet, we're able to monitor that and alarm that at our, through our software called Navigator, which we monitor that to a couple monitoring centers around the world 24 hours a day, 365 days a year. So demand flow does not sacrifice comfort for energy savings. We simplify the operations, typically in a plant. It wasn't uncommon. In fact, one of our old methods for optimizing plants was to understand the sweet spot of a chiller, and I always try to run that chiller within the sweet spot, right? Which meant, though, depending on what your load was in the building, you may be running more equipment than you really needed to, but you're running it to stay within the sweet spot of that equipment. Demand flow, as we vary the flow through the evaporator and condenser, essentially we flatten out the efficiency curve of a chiller. So what we do is we typically just will run one machine up until it's 85, 90% loaded for a period of time. And then as the load increases, say, okay, load's continuing to go up, let's bring on the second machine and the third machine and fourth machine. And it's just the opposite as load starts to drop. Now, could we save additional money by continuing to manage this through sweet spot management? Yes. There's a little bit of savings extra to be had. But the operational savings from the standpoint of the ease of understanding what's happening in your plant, we feel is a bigger benefit. However, if a customer says, no, I want to optimize this, I want every kWh that I can possibly save, then we will do it. But we definitely believe the simpler the operation, the better. We reduce energy consumption. Obviously, we provide chilled water for less money. We extend the equipment life. And this is an interesting conversation that we have a lot of times with the customers. But if you consider that we're putting VFDs on every single piece of equipment, and that pump that used to be a constant speed pump, delivering at constant speed, we're now operating that pump quite a bit less. So the shaft miles on that pump are going to be reduced greatly, which just is going to extend the life of that equipment. There's less maintenance as well. Again, reduced load, less wear and tear on that equipment. It's just, a natural conclusion. We have had a couple customers ask us then to prove that. So we did some engineering studies where we look at shaft miles on motors and we calculate that and we provide that information. But most customers, pretty well understood, and they agreed to that. Here's an example of a project we did. I'm going to be real honest with you. I simplified the numbers just to make it easier for me from a math standpoint, but it's pretty close to what was actually occurred on the project. This was for a plant, an IBM plant in outside of Raleigh, North Carolina. And it was a $300,000 project, and we were saving about $100,000 a year, so simple payback, 3 years, thereabouts. However, when you add our service and the measurement and verification, the ongoing measurement and verification, it came back a little bit greater than 3 years. However, after we did the project qualified for a $230,000 rebate from Duke Energy. So essentially the payback was dramatically reduced. We went from an average 0.89 kW per ton to about 0.61. They had an ice storage system on the plant at the factory, and we improved the thermal storage system. Not really anything we did to it, just the fact that we're slowing down the water when we could meant instead of having a 2-hour tank, they were getting approximately 4 hours from that tank. So they're able to keep an additional chiller offline 2 hours more per day for every time that chiller was going to run. And this project came out to be about a 2-year simple payback. So some typical questions that I have. These are ones that normally come. Will demand flow work with magnetic bearing chillers? Yes. We did a project not too long ago with McQuay, or Daikin, I should say, in which they supplied their magnetic bearing machines, and we had a demand flow project there. And we took their machine, improved the efficiency on that machine by about 35% over its rated efficiency for the year. When you think about what makes a magnetic bearing machine so efficient, it has nothing to do with the flow of water through the machines, right? It's all bearing related. So definitely it works. Does demand flow prevent surging on the machines? Yes, we do. So how do we do that? We essentially are managing the lift of that machine. And the way that we manage it is by either speeding up or slowing down the water going through that machine. In doing so, we can manage the delta T between the evaporator barrel and the condenser barrel. Because we know that the entering water into your condenser, from your condenser into your chiller, and the leaving water from your chiller going to your building, that difference is your lift. So when we understand what the minimum lift is for a machine, we essentially just change the flow of the speed of those pumps to maintain that lift, whatever that minimum plus whatever safety factor we want to have on the project. In doing so, we keep that machine operating just above its surge line. If you do that and you do that well, that's the optimal place to run that machine, right? So you prevent that machine from surging, but you also have optimized the conditions for that plant at the same time. Will demand flow work with machines with surge mapping? I don't know if all of you understand this, but newer machines now have essentially memory in the machine that when a machine surges, it records what conditions that machine is operating at when the machine started to surge. And in the future, as it starts to see the conditions that machine is operating at approaching that limit, it essentially prevents the machine from loading up any further and prevents it from surging, which is a great, great idea, except for the fact that in many places we go out where customers bought 2,000-ton machine, 1,000-ton machine, whatever, and you realize that they had a problem with surging at one time, and maybe it was surged at 70% of its load. That machine, from that point on, is limited to 70% of the load of the rated load of that machine. So effectively, you've changed a 1,000-ton machine into a 700-ton machine. So you're treating the symptom, but not the cause. So the first thing we have to do on a project where we see we have this surge mapping is we have to clear the surge map. We can't do it without the chiller manufacturer. It requires special software that they have. But essentially, that's how that works. But yes, and you'd be surprised the number of customers we've said, hey, you realize that that machine's operating at max 70%, and they have no idea. Will demand flow work with non-Siemens systems? Yes, as long as your BMS system is BACnet compatible. If you have PLCs, we work with PLCs as well. We'll work with other companies other than Siemens to implement. So, for instance, the Nashville Airport was actually a ESCO competitor of ours that won that project but wanted to put demand flow in, and we worked with them on that project. So, will demand flow improve the efficiency of variable primary plant? And the reason that question's in there is because we hear this quite a lot from consultants who tell us that, hey, my plant's already variable primary, you can't do much to improve the efficiency. And it's true, there's not as much efficiency gain, but typically anywhere between 10 and 15% we can improve the efficiency of that system. And essentially what we're doing is varying the set point instead of operating off of a fixed set point from a pressure standpoint. Generally speaking, variable primary plants are pretty darn efficient to begin with, but there's still work that can be done with them. Can demand flow be installed on new construction projects? Yes. We essentially are able to model based on the engineer's design data and build a model to predict what the KW per ton would be. And then we do the same thing that we do on any other project, and then we do the calculations again using the demand flow model. And that difference, that efficiency gain, we will guarantee for the first year of operation. Now, in the US, we guarantee about 20% of the projects that we do. Internationally, it's 100%. Don't know why it's different internationally, but every one of the projects we've done, they've required a guarantee. And we're happy to do it, but don't understand the rationale. Will we work with absorber machines? We will work with a plant that has an absorber machine, but obviously you have to be very careful when you start reducing the flows through an absorber. You'll crystallize it in a heartbeat, right? So what we will do is once we get above certain load levels, let's say we have 1,500 tons worth of refrigeration requirement and we have a 1,000-ton absorber. Well, we can turn that absorber on, and then even if we're reducing the flow a little bit here and there, that machine will still have enough flow to prevent it from causing any problems. But if it's an absorber machine all by itself, no, we can't do anything with absorbers at this time. Can demand flow work with existing sequences of operations, or do you have to write the SO? Do we insist on our own sequence of operation? I would say probably the vast majority of the times we go into a facility, an existing facility, their sequence of operations are pretty good. However, if we find that, if we changed it a little bit, that we can improve the optimization of the plant, we will certainly make recommendations to do so. It's not uncommon when we walk into plants and you have 3, 4, 5 machines of different varieties and different efficiencies. And customers used to always start chiller number 1, then chiller number 2, and those were the 2 most inefficient chillers in the plant. So we talk about what it is that they want to achieve and how we can improve the sequence of operation if they'll let us. So the answer to that question is it really depends on the sequence of operation and the customer. But if a customer tells us absolutely not, you're not going to change anything, we have, that's the parameters we have to live within. But we have to then calculate the savings based on that sequence of operation. How many projects has demand flow been installed on? We're approaching 400 now. By the end of this year, we expect it to be somewhere around 450. How does demand flow work with pressure-independent control valves? And we found out the answer to this question the hard way. We were fortunate enough to be involved with the Smithsonian Museum project in Washington, the new one, the Museum of African American Culture and History. And we were commissioning the project, and everything was working great, and then the load started to drop, and demand flow responded by slowing down the pumps. And the pressure in the system went below 5 pounds. And at that point, we started seeing the delta T's going crazy. It was bouncing all over the place, and we said, what is going on? And we realized that what it was the PIC valves. The pressure-independent valves have a requirement to maintain at least 5 pounds of pressure in the system for those to work properly. And as soon as we started going below 5 pounds, they stopped working properly. So the answer is, okay, even though we could have slowed down the pumps more and we could have achieved even more energy savings, we couldn't do it. The disappointing of that particular project is we sold them the PIC valves. And honestly, you know, when you have a demand flow project, they're not necessary. And those are hugely expensive valves. Not to mention the setup time on them is much more, maintenance. They're great, don't get me wrong. But in this instance, from at least the water side savings, they had a negative impact on us. Not much. Probably about 4 or 5%, but significant. I just got one other thing, because one of the questions or the agenda items was, you know, what obstacles do we see to implementing demand flow? And typically, it is maintenance on facilities. We'll go into plants and we see chillers that, quite frankly, aren't working well at all. You know, have approach temperatures on them, 3, 4, 5 degrees, 6 degrees, which is an indication that you're either low on refrigerant or you've got other problems in that machine. And as we start to vary the flow through those machines that are not working well, the machines struggle to deliver a constant set point. Constant 40-degree water, 38, whatever that set point is. You will see that as you start reducing the flow. If the machine is fully charged, you don't see that at all. It's no problem. The other problem that we see is the air side, because we want to eliminate all forms of bypass. So three-way valves, we're going to get rid of them, okay, or close the bottom port. Bypass, we are essentially making, like I said, one continuous loop. So bypass is our enemy. So three-way valves. And it's not uncommon we see air handling units that the units are not tuned from a control standpoint. So the chilled water valve's going from open to close to open to close over a few minute span. It's able to maintain 55 degrees just by luck, but essentially during that time when that valve is wide open, we're dumping that water, that chilled water, right through that coil, right back into the return, and it hasn't done any work. That valve essentially is a bypass at that time. So one of the first things we always do on every project is have to start at the air side. Are the loops tuned? And we have to tune those loops in. Otherwise, it's very hard to optimize the chilled water plant, because if the air handling units are bouncing up and down, guess what's happening in the plant? It's following that same cycle. We can see it in the temperatures that are coming back to the plant. So essentially, that is what we do with demand flow. Like I said, there's a number of solutions on the market. Quite frankly, if you haven't done optimization in a facility, or if you have customers who haven't done it, that's our biggest competitor. The customer who just doesn't understand where the savings is coming from. Sometimes when you tell someone that, you know, sounds too good to be true, they believe it, you know. This can't be right. We face many customers who say, hey, I've been in this building for 20 some odd years. I run it. I know how it works. It can't get any better than what we've done. And then we implement, and, you know, it's usually a pretty good day.